All right. Hello, everybody. I think we are just 2 minutes over, but how about we get started? Um, so we will kick this. Oh, okay. I'm just gonna hand it over. Let's not waste any time. Go for it. No, it's okay. I think the only thing I was gonna say is, again, reminder, this is supposed to be a discussion, so let's all engage. That would be great. Thanks.
Okay, thanks for the introduction. Once again, my name is Peter Graskowski. I'm here at Oak Ridge, and the point of this talk is going to be tying this quantum error correction a little bit to this general idea of workflows that we've been talking about. So my understanding is that some significant fraction of us probably don't think about quantum error correction day to day. So I'll start with a couple of slides that are kind of a little bit of an introduction. So as we probably all know, quantum error correction provides a means to tolerate and ultimately overcome the effects of errors. The idea, of course, is that we, instead of utilizing a sort of a noisy physical qubit, we sort of take a whole bunch of noisy physical qubits and we make a logical qubit out of them. These logical qubits will still suffer errors, but now the information is spread in some non-local way. And so even though the qubit, the individual physical qubits suffer errors, we can still hopefully detect them and then correct them. So typically with this quantum error correction codes, you sort of parameterize them by 3 different numbers: the number of physical qubits, logical qubits, and then the distance, which is basically a measure of how many errors you can effectively tolerate. And so, so kind of high level, you sort of want not too many and to be not too large, right? Because it's a resource you have to provide. You want K to be large because you want to encode lots of logical qubits in there, and you want also D to be large because you want to tolerate more errors. Now, unfortunately, there's some bounds between these numbers. They're all sort of, related to each other. So there are limits on what you can do, but nevertheless, at a high level, that's sort of what people aim for. But I don't know if it's a problem, maybe it's not a problem, but it's interesting observation is that there's no such thing as really best code for everyone. There are different hardware resources constraints, different noise types, gate locality, some logical, in some codes, logical errors are easier than others. So one example of this is, in fact, if you consider, let's say, superconducting circuits, and you can think about what Alice and Bob is doing versus what, let's say, IBM or IQM are doing, the hardware, even though it's still superconducting circuits, the hardware is susceptible to very different types of noise. So the error correcting codes that they will utilize will be very different. Therefore, the sort of underlying architecture will also be different. So that's the punchline. Different architectures, quantum error correction codes will have different specific requirements. So this is a super high level overview, a big picture of sort of how to implement a quantum error correcting code. Once again, this is like a loop that you can think about running indefinitely for the lifetime of the experiment. So once again, you have a quantum computer. I apologize for my graphics. I am artistically challenged. But so you have, a whole bunch of physical qubits. You've sort of defined how you're going to define your logical qubits among them. And then there's sort of a few things that you have to do. First thing you have to do, you have to make what we call a syndrome measurement. So that effectively means doing like a sort of a parity measurement. So you have to measure operators such as ZZZ or XXX on some number of qubits. In most architectures, you cannot do this directly. So instead, we sort of run a circuit like this where you have some data qubits that are encoding your actual logical data, but then you introduce extra ancilla qubits, and then you perform these 2 qubit gates between them. And you measure the ancilla, and that gives you the sort of measurement that you're after. So this syndrome tells you something about where errors have occurred, sort of. But then you have to pass them into some classical computing infrastructure. And that infrastructure is running a device called a decoder, a syndrome decoder. So the decoder basically takes the syndrome data and then converts it into it converts it into operations that will perform corrections, right? So they undo. The syndrome tells you how to undo the errors that have happened. So for small error correcting codes, this is actually very simple. Sometimes you can have even a lookup table. For larger, as you sort of grow and you utilize more qubits, then these become more complicated, and you actually have to do some sort of a computation. Okay, so that's a classical computation that in general has to be done. And then the next step is applying the corrections and fixing the errors that have occurred. There's some caveats around it. One is that these corrections can typically be deferred. I'll say a little bit more about it on the next slide. So let me sort of connect memory versus logic. So I just want to highlight that everything I've talked about here right now, it's really just sustaining this logical qubit. Okay, we haven't actually done any logic. We've done these circuits, but the circuits are not doing any logical operations. They're just making sure that the qubit stays alive. So if all you want to do that, then we sort of call this just logical memory. And it turns out that in this case, both correction and the decoding can actually be deferred to the end of the sort of quote unquote computation. You're not really computing, but you're just letting the qubit live for long. The qubit will lose its quantumness, but if as long as you're reading these syndromes constantly, you can sort of correct everything at the end after you've read out the actual logical qubit, okay? But that's not really what we care about long term. What we want to do is we want to do actual computations, again, at the logical level. So, this is some circuit that we might want to run. Again, think of these qubits now as being logical qubits, each of them corresponding to some number of physical qubits. So in practice, you then have to sort of fit these logical operations between the cycles of your actual quantum error correcting protocols, right? And now in order to then do this computation, you sort of have to define a logical universal gate set. So number of logical gates that will let you implement completely arbitrary algorithms. So this is a little bit hairy, but like they're sort of, you can divide them into two types. So some are Cliffords and then non-Cliffords. And I'm just giving you an example of one particular set of universal gates. There are many others that people can think about using. And there's a sort of an important difference. So with Clifford operations, both the corrections and decoding can actually be also deferred. But non-Cliffords, that's no longer the case. With non-Clifford gates, you actually have to have done at the very least the real-time decoding. So before, so say you do you have an Clifford operation, non-Clifford operation that you want to do, you have to have sort of decoded up to that point. Okay. The correction is still optional, but there are some circumstances under which people still think about applying corrections directly, okay? But the point is that because you now have to do at the very least this decoding, what that increases the constraints on the latency of the implementation. So just a few sort of high-level points. So what are the timing requirements associated with this? I'll give you actual numbers for some particular experiment in a second, but here just highlight that, of course, that depends on the details of the architecture, quantum error correction code, and so on. But you want to do it fast enough so the errors don't overwhelm your computer. Question? Yeah. So this. I didn't know this. I had recently been just looking into this. So this bit here, there's a paradigm by which I can basically delay this until the end. So I have to know I have to basically do the decoding. Once I know the decoding, I sort of know how to apply my T-gate. Yeah.
I meant for the, sorry, thank you. I meant for the T-gate, not for the Cliffords.
Yeah, so I even mean this is true for the T-gates.
But isn't there branching conditional on?
Yeah, so you have to, that's why you have to have known, by knowing what the decoding has done, by knowing what the correction is, you can basically choose how you implement the T-gate. So this is defined in this 2019 paper by Daniel, forget the last name.
Oh, Litinsky?
Litinsky, yeah.
Okay. So you're moving to this Pauli-based computation formalism, is it?
Effectively, yeah, I think you can think of it like this.
Okay, let me think. I think you can't do branching indefinitely, but we should.
Yeah, so we can talk about this more. I also didn't know about this, so I sort of went on a bender looking at some number of papers, and I think this is in fact true. Now, there are cases where it's not clear that this is actually what you would do, because once you have to put in the time to do the decoding, it may be that the applying the gates directly is just a small fraction of the classical compute, because you just have to generate your pulses and so on. So exactly, yeah. Any other questions about this? Okay. Yeah. So you have to do this sort of fast enough that you don't get overwhelmed by the errors. So some number of sort of timescales and constraints that one has to keep in mind when defining this. Qubit coherence, again, not too many. Your qubits cannot be too noisy. If they're too noisy, you have too many errors happening before you kind of can even read the syndrome out, then things are going to fail. You're not going to be able to correct them. You have to be able to do this gate readout and initialization fast enough, because you still have to run that syndrome extraction circuits, the classical processing, the coding, and then if you're applying a active correction, pulse generation, that has to happen fast enough. And then you have to pass all the data around. So basically, to sort of figure out whether you've got all the right infrastructure in place, you have to take all of these things into the account. And so I would argue that sort of in contrast to the most application workflows that we discussed in the morning, one presumably needs somewhat more specialized hardware, right? At the very least for the decoding, I think this is widely believed now that people will need some sort of FPGAs or maybe GPUs that are living very close to the hardware. So I wanted to, yep.
FPGAs and sorry. The whole thing about the FPGAs and the GPUs. I mean, do you think that today's GPUs or the current roadmap of GPUs are going to be able to handle this, or are we kind of looking at like a ASICs GPU of some sort?
So. I mean, ultimately, the type of decoding that you have to do depends sort of on the size of the syndrome count that you have. So even today, and I will show you in my next slide, literally an example where using sort of off-the-shelf FPGA, the decoding can be done in a fraction in 100 nanoseconds or something like this. Certainly the GPUs that you can get, something like Frontier, that can do enormous amount of coding. I would imagine that actually it's a combination of things that one has to worry about. So both the time, the decoding time, but also some of the other sort of classical compute that is involved. And also the shuffling of the data around. So I'll give you so maybe after this slide I'll give you actual numbers of this experiment. So I did want to show you one particular
question back here.
It was more of a comment because I do assume this is a discussion session. Sorry. I think GPUs are generally slow to decode, right? They have the latency requirements are the latencies are very slow with them. And it depends whether you're decoding surface codes or LDPC codes also. So I think the fastest ones I've seen is FPGAs, but also CPUs, surprisingly.
Yeah, so I would sort of differentiate a couple things. So one is the latency associated with basically putting the data into the GPU versus the decoding capability of a GPU, right? Certainly if you ask NVIDIA, then there's no issue with none of those things. So I think it's still sort of, I think it's not clear what people will end up utilizing down the road, but there are approaches where people are using GPUs, like NVIDIA, the recent NVIDIA paper from a couple months ago. This is what they propose. And there are cases, which I'm going to talk about here, where you just use a standard FPGA. Okay, so I was sort of debating as to what experiment to discuss here. And there's, some people are probably in a room that have been responsible or behind some of the experiments that have been done from some of these companies here. I sort of decided in the end, I'll just look at whatever is maybe the latest. So this is a paper actually out of China. But what they do is they basically engineer the whole loop that I've described above, even including the active feedback, what they call is just this active correction. And they do this for a surface code. So this is superconducting circuits. They consider it a D3, so distance 3 patch. So you have essentially 9 data qubits. You have 8 ancilla qubits here. So you have to run these circuits that I've described. So you initially run the circuits. That gives you the syndrome measurement. The syndrome is passed into what they call central feedback module. So that is the thing that contains the FPGA that implements the decoder, the neural network decoder in hardware. They do the decoding, then they, in some experiments, one version of the experiment, they pass that onto these pulse generators. The pulse generators generate the pulses are then sent back to the chip. So this is the actual results that they show. So you can plotting essentially fidelity of some initial state versus the rounds of this error correction, the number of cycles that they've implemented. So this is still just a memory experiment, but in one variant. So you can look at the the red curve, they actually do apply this active correction, okay, directly. So they're not applying any gates, any logical gates, but they're applying the correction. They're fixing the errors. And you can see, so if they're doing nothing, then it's the blue curve. So the fidelity is lower than if they do something. And again, the green is if it's when they sort of shift the correction and the decoding until after the the full experiment. So these are some numbers, and sorry, this is probably a little bit small, but the classical only cycle time, which involves all those things that So was mentioning, that's why I was mentioning earlier, it's not just decoding, it's a whole bunch of other stuff that has to happen. You have to pass the data around, you have to initialize things. So that takes half a microsecond for them. And then the quantum part, which means running the extraction, the syndrome extraction circuit, that takes about 1.2 microseconds. So the full cycle for them is just under 2 microseconds, which is I've sort of try to compare to some of the other results, and that is really state of the art. Yeah, so QEC sort of improves performance versus doing nothing here, and they do talk a little bit about some limited non-Clifford operations, but please read the paper if you're interested. And I think these are my, I'm sort of done now. Maybe I'm not going to go through all of it, just highlight that. So the QEC does not directly fall under any of these application workflows that we've discussed earlier, but because sort of the application will run on top of anything that's being done here. But there's certainly some overlap. One needs to this interleave interaction between the quantum and classical hardware. And I'll skip all of these, but maybe one, for the sake of discussion, one point that I might sort of ask, down the road, presumably, once the technology advances, we can imagine a world where the application developers don't have to care at all about the quantum error correction that's sort of happening underneath, right? You will just define your circuits, or maybe even some higher level programming language in terms of, let's say, some logical gates, and you sort of pass it on, and then the hardware, the error correction just happens. But I sort of wonder, because that it might take a while before we get there, but I sort of wonder whether there are cases to think about where you sort of define an application, and then you define some sort of quantum error correcting code, but you sort of combine the interaction a little bit more closely, right? You have to think about the details of how the error correction is done, but it's tailored towards the application. But so yeah, so the question is whether we can actually gain something from that, certainly and in particular in the short term. And I think I'll stop here. Yeah.
Great. Any questions?
Test. Okay. It's maybe a little out of scope, but I was just thinking. But when you look at all that, like the last paper you showed out of China, I've seen some work where people are trying to squeeze a little bit more out of this whole process and using syndrome data not just for QEC but also for calibration. And I was just wondering if you've seen that too, if you thought about the added complexities, but the kind of the nice two birds, almost one stone, that sort of approach.
Yeah, so I personally haven't seen this, but that would very much fall under some version of this, right? Where you sort of you utilize something else besides error correction. Like you think about the error correction, but you also think about the overarching goal, which could be calibration or could be particular application or whatever, right?
I have two questions, I think. So the first one, by the way, very nice talk, and thanks that you laid out the workflow itself so nicely for that case. So I understand you're right that this does not necessarily fall under this classical HPC QC case, right? But how can you project how an end user workflow could probably have to interface with this?
Yeah, I mean, so in the long term, the direct interfacing, I think, will be minimal, right? Like you sort of once one implements this underlying fault tolerance and quantum error correcting mechanisms, then the user or the application layer doesn't sort of directly have to know anything about it. It just says, I need to run this circuit. This is the logical version of the circuit. some hardware below has to figure out, some software hardware has to figure out how to run this.
But isn't it like, so I think this is a paper from IBM or so, I think, so where they talk about their hierarchical error correction. And so if I have fully understood it, that the argument there is that at higher levels, you probably have application specific correction routines that improve the overall workflow.
Right. So okay, I haven't seen that paper, but that then again falls in some version of this here. I just meant in the long term, presumably that will just not be the case. My guess is because you won't have to, but in the short term, yes, some version of kind of connecting the two. But I don't know this IBM's work, so maybe somebody else can chime in.
Okay, well, actually, just a super quick follow up on that part.
Yep.
The when you say that near term, it may be an issue. The error correction, application specific error correction components that we have to account for near term. So I'm just kind of curious why only near term. And then he was discussing the workflow layer for the user. I'm kind of curious about the hardware level. So if you've got classical, I'm sorry, excuse me, if you've got classical hardware that is dedicated to keeping the quantum system healthy and alive and dealing with the error correction, the decoding, all of those components, and then you've got classical over here for the application side, if there is any sort of dependency, right, for the application specific error correction, right, then that would suggest that latency is going to become a big issue quickly, or is it? And does locality then become an issue because of that parameter?
So I mean, the first question was why only in the long term that why in the long term you might not need this sort of direct integration. This is, I mean, the long term might be very long term, right? This is the argument is sort of, to me at least, a little bit like this is for the same reason that we don't have to write assembly anymore, right? That there's like the underlying, yeah, absolutely, right. So like it's everything is good enough and fast enough that the application developer doesn't have to worry about those details. They just think about the logic of the application.
From what Sebastian and Laura were saying and asking, I think like in the near term, the user might specify the required accuracy, which would change the QEC code that might be used, and then latency might become a problem, like Laura said.
I get a quick comment in. So what I can imagine is something like from classical software, for example, we have configurable parameters for error correction depending on the type of application, because we are well aware, like in current systems, for example, in RAID systems, we have like RAID 0, RAID 1, 0 plus 1, and whatnot.
Mm-hmm.
And depending on what you need, you would have then, okay, I want surface code for this part of application, I want color code for this part. I can imagine this in the short term, and might still be in the midterm a problem where people actually want to exchange stuff themselves to figure out something better.
Mm-hmm.
This is something that we usually keep disregarding because we just assume error correction will be solved at one point. But I think this will be a very long time until it's actually in a state where it's completely solved.
Yeah, I think I totally agree. That's a good point. And sort of connecting this to Laura's point earlier, you know, like having active error correction that necessarily puts this constraint that is sort of not directly seen in some of the application layers that we've talked about so far, outside of, say, this mid-circuit measurement story, right? Where there is a sort of a hard time requirement that at the very least the decoding has to happen, right? So if that's the case, then sort of connects to our previous discussion. What implication does that have on having the machine living close to the sort of classical infrastructure?
Sorry, this is one of the things that I'm always getting confused in my head. So when we say classical, can we kind of the error correction classical and the application classical? Because what you're talking about right now is the
I mean, I was sort of referring to both to some extent, but yeah, I was mainly thinking about the classical related to the quantum error correction. So so this stuff here. Right, presumably this stuff here, if the latencies are really have to be that small of order, hundreds of nanoseconds, let's say, or something, then presumably you actually really need the classical hardware, this classical hardware, the FPGAs or GPUs or whatever, to really live very close by. But then on the other hand, if we say, okay, let's suppose that's true, and then we really abstract away quantum error correction from the logical operations, then maybe the classical computer can live elsewhere because now it doesn't matter anymore, and that's a long-term thing. But if in the short term,
the error correction or the
application layer can live somewhere else.
Sorry.
But now if we're really thinking about this here, where the application layer now knows something about the error correction, and then maybe it has to therefore inherit some of the latencies that are associated with the slow latencies associated with the need for running quantum error correction, that maybe that induces a constraint that the classical application hardware also have to be somehow close by.
So, I mean, this is a really important point, I feel, because we're making design decisions. I mean, there's this kind of this overwhelming point that the HPC system, that the applications part can be anywhere, the quantum can be here, et cetera, and they're basing that on like performance data for the between the quantum and the HPC, for that part. But thinking about this parameter and this layer, if this does become a dependency, this literally changes how we place systems.
Yeah.
And so this is significant. And I'm hoping that on our ecosystem, we're going to have a portfolio of setups, right? So we're going to have some that are going to be co-located, with whatever distance we're talking about. Some of them may be remote, and then depending on application, there may be certain systems that you have to go into because of whatever issues that you have. But I'm trying to think how you mentioned the IBM one. Is there other how can we push on this? Because this is kind of one of those points that we need to kind of at least have a idea a little bit, not a that it's we have to not have a hard no. At this point, we have to say, this is something that we actually really do have to pay attention to. At what point, what do we need to do to get there quickly?
Maybe I can make a few comments exactly about that. So first, actually, I really like this idea of QEC application co-design, because one of the big problems we are interested in is simulating Hamiltonians, is trotterized simulation of Hamiltonians, for example. And most Hamiltonians we're interested in simulating, they have translation invariance. So what ends up happening is that you can build error correcting codes that use the translation invariance of the Hamiltonian to, in their code automorphisms and so on. So there's some really nice work from Coera recently where they use this to basically co-design QEC LDPC codes together with the Hamiltonian simulation problem they're interested in. So that's the first. So it's not really like, oh, maybe. I think this is how future applications, fault-tolerant applications, should be developed. So I think it's a very important point, and I agree with Laura. The second thing is, I think part of the trouble is that I don't think all QPU vendors are interested in exposing their error correction layer and error correction stack. And I understand that, maybe you're running some sort of gross code underneath, and they let you run some concatenated, some simple classical code on top. These are real problems, but I do think that the kind of original model that I saw from Chris this morning, where you have a small HPC tightly coupled to a computer, co-located, tightly coupled, and then a larger HPC on campus, slightly loosely coupled. This solves a lot of these problems because, okay, let's say you want to use a different kind of decoder, you activate the GPUs in your nearby small HPC system. Please.
So one thing I would really like the large scale HPC folks to weigh in on this localized snowball HPC system next to a quant. I mean, because I mean I know I've heard that model too, that we place a moderate size application based HPC with the quantum and the classical error correction and all of that, and then you pipe there. But when we're thinking about I mean, and maybe it works, I don't know, but I would really want some large scale folks to weigh in on that, if that would work with some of their runs.
Perfect. And maybe I'll make one more quick comment while the mics move around, which is that if you don't enable these things, then I don't think there is much QEC R&D you can do other than just simulating circuit level noise on your computer and doing things by pen and paper. So if you really want real experiments, I think you do have to enable the GPUs, the CPUs, the FPGAs in a nearby HPC rack to interact with your QPU and actually do experiments rather than just hard code the error correction layer into that, which I understand the reasoning for, but I don't think that's the right model at the moment.
A comment to what you just said, and I think, I mean, I might be totally wrong, right? It's really just what I believe I have understood, but I think it's really worth that we are precise here. So the way I understood Chris in his talk, the co-located small or medium-sized HPC system would not be sufficient for the error correction. I don't know if you can confirm that, Peter.
I mean, I would imagine that you'd still need to have some FPGA or something, right?
Exactly.
It's super low latency. But then maybe you would have the sort of the closer interaction with some co-located HPC system, let's say, that would somehow maybe, I mean, I don't know what that would look like, Ravi. Probably, in fact, if you've read the IBM's paper, maybe that's the first place to look at.
I was trying to look it up, but
Peter, can you go to the latency, the networking latency of this thing?
This one here?
Yeah, this one, yeah. Do we have a sense of how long it takes to send the syndrome data to the decoder?
Yeah, so so they define this as syndrome calculation. So that is, I think, that's related somehow to something that happens after running the sort of the last step of the circuit, and then before things get passed to the actual decoder. So that's 20 nanoseconds. I mean, it's all of order 100 nanoseconds at most, let's say, right? According to this.
And what Chris said, I mean, his co-located, tightly coupled HPC, if I remember correctly, he was talking about 1 to 10 microseconds.
Yeah, that's what I was actually going to say.
So this is what I mean, right? So we have actually these 3 time scales.
Yeah, so that won't solve the problem. I agree.
I think quick comment. I think the one part of the IBM paper was showing that they can do the error correction on the ASICs in time, right? But again, this is specific to superconducting qubits only because they are so fast. So depending on what kind of platform you choose, you might have a different type of scenario. Because I think at Continuum we have done this showcase where we had a NVIDIA rack that is mimicking the snowball system, doing the decoding for our system because the latency matters a lot less for us.
Maybe I'll make a quick comment. It's not just superconducting qubits, it's also spin qubits. They also have
of course.
Slowly we are getting to larger families, right? So I don't think we can just be like, oh, it's one modality's problem only.
I just want to jump in, Laura, for the question that you had about, now we're starting to talk about setting up small piles of HPC systems. I think that comes down to a discussion we were having this morning is what do we define as tightly coupled and what's loosely coupled? If they are tightly coupled, you don't need to have this small pile of HPC resources. You could reach into the bigger pile and do the work there. So that's where I think we may want to take time as a group here and figure out what does tightly coupled mean, what does loosely coupled mean, and then we can start to say, okay, on this loosely coupled one, yes, you might need something very localized, very low latency, high bandwidth to be able to do this.
So sorry. So coupling equals latency.
Well, it's a more coupling is a really broad term. So
Right.
coupling would be
coupling and
bandwidth,
integration is
latency.
something we have to work on, I think.
Right.
Yeah.
Yeah. And that's where I think we need to, I think part of our group here, we should think about making a better definition for that. So think about here on campus, you've got Frontier sitting in one building, you've got the IQM machine sitting in another building. Is that a tightly coupled because they're on the same campus? Or do they have to be in the same building, in the same room? Maybe we can collaboratively put together a first cut at that.
Yeah, and I mean, so this is a point Amir and I we talked about the coupling, the integration, the use of and the latency. I mean, there's been a couple of papers that have like defined, and we kind of need to kind of coalesce all of those, because the other thing, and I didn't mention this in my talk, but when I was listening to Gina and Rick Stevens and all at the Genesis thing, they're talking about in that whole HPC AI, they're talking about tight integration, right? And what they mean by tight integration, kind of on this, this federated model. And all, I mean, they're talking about like policy alignment, administrative alignment, and I mean, we can have a supercomputer in building A and a quantum computer in building B, and if the networking's not running or something, then you're going to have weird handshake, and section points. Do you know what I mean? And so it's administratively a lot easier when everything is on the same network, when it's on the same when it's administered by the same people, and the updates to the software on both sides, or and all of that's aligned. That really affects the end-to-end workflow, right? So to me, that is tightly integrated when it kind of hits on several different levels, right? And then the coupling versus, I don't even know if maybe we should just kill coupling, I don't know, and then latency and integration, something like that. But I agree. I think that's something that we really have to work out, because I see a lot of people getting really ruffled feathers on the integration argument when we're actually talking about different definitions of it.
I agree. Let's start to make that definition. Let's create the vocabulary necessary that we all can have the same conversations, or at least similar enough.
Any other comments, thoughts on that?
I mean, I'm really excited by this, and it's just so, to me, it's so important. How do we build a structured attack on figuring this out? Do we take one target application and try to run it through several different models and see, where it would break, try to do that exercise, or, really, how can we do this? Because I mean, the whole thing with my talk, the locality, the workflows, the administration, all this stuff. So, there's a model. Can we just have an application, run it through model A, where this system's here, these, this, it's run by this sysadmin and this update schedule and this and that and the other, and this is the policy and this is the worker and this is the manager. I mean, I know it's kind of banal to the really exciting technical work, with the quantum and the HPC and the scheduling and all of that, but that's what's going to break the workflows. So how do we attack it? I'd be super excited to do it, but we got to do it as a community.
All right, so as the moderator, I'm just going to volunteer the other moderators to take the action on that. So I think that's Laura, you, me, Sebastian, and everyone else. So that's it, right? There's only 4 of us.
Here,
for this particular work
I
stream,
think
right? We can
Johannes-
take the action on the work stream. Yeah. Let's take the action to come up with and let's come up with. I think we do is we summarize it as something where we need to come up with a short-term action to start moving forward. Yeah.
I'll just point out that the part of this group is really actually sort of in the mission of this group is defining that those terms, and some of the meetings that we started having that Johannes is leading again, who couldn't actually be here. That's sort of like part of the game. So we started writing something out, but it is indeed a major problem, and we find this that every time we talk to somebody else, they sort of see the story from a slightly different angle. And part of this is because their application they're concentrating on is maybe different, or maybe the hardware that they have has different end requirements. So it's sort of tricky to get everybody on board, but that's the goal.
Great. Okay. Any other questions? Yeah, here we go.
Sorry, my mind is now thinking. So, as I mentioned with the blueprint and the idea of 2028, to if a system is there and at certain level of fault tolerant and whatever, what sort of application if they do that. Again, it's one of those that I really want to push on. Let's try to figure out, or at least get a better idea about application specific error correction dependencies and all of that, because and try to do it sooner rather than later, because again, I think with the push that we have in the community, does the locality do certain things actually make a difference? And we should try to have some sort of an answer to that before systems get seeded, larger systems and stuff.
Maybe I'll also make a follow up of that, which is that I think we have we have now a few very well identified applications, right? Simulating Fermi Hubbard for material science, quantum chemistry, cryptography, and a few others. But we also have very good emergent error correction codes, like surface code by now is very well understood, but also families of LDPC codes are being very well understood. But one of the things I haven't seen enough of is understanding the decoding requirements of LDPC codes, and in particular the hardware requirements, right? So as I think Peter was originally saying, depending on what you do this decoding on, you have different hardware hungry solutions. And I think getting a better sense of what those look like together with the application. So going back to the co-design, like pick your 3 favorite applications, pick your 3 favorite error correcting codes, do analysis of how they pair up and what the requirements are.
Could you go into a little bit more detail about, you said we don't know, is it the size requirements, what do you mean?
So what happens is that usually when we say, oh, this classical hardware is responsible for the decoding of the error correction, that's the one that is right next door to it and kind of plugged into the QPU. What they're running is some class of algorithms which look something like minimum weight perfect matching, or they're a class of algorithms that we run, and we have a pretty good understanding of how hard they are to solve for specific error correction codes. But as you change the error correction codes, the time to solution for those things, how much time the decoder will take to solve the decoding problem, tell you what correction you should apply, varies quite a bit. Mm-hmm. And so getting a better this is like a performance profiling of your decoder. And that's what we need to understand better for LDPC codes. That's the statement.
Mm-hmm. Okay, thank you.
And to add to his point, basically, we have machine learning solutions most of the times for these decoders, right? We have lookup tables and we have reinforcement learning agents. So we would have to look at, other than those requirements, we would have to look at different types of qubits. We would have to look at different types of parameters these models can handle. So thinking of the data plane, control plane, yeah, we have to understand the latencies there as well. And that's something we should consider maybe in our notes too. So, I mean, there are different, like for example, for FPGA, we have different decoders, but for GPUs, we have different decoders. And for ASICs, there are different requirements of the decoders. And some of these come with, like in terms of FPGA, we would have to consider the DPU blocks. And so hardware level configurations are different for each of these models, how we are fitting them in, how we are running training them. So everything changes if it is depending on the hardware, like the classical hardware. So we will have to do the training also accordingly.
I don't know if there is an audio for virtual attendance.
I think we can hear you. It's coming
Okay.
from above. I
Yeah.
think it's from Zoom.
Yeah. So I just want to mention that there is another dimension to this. When you consider real-time decoding, there are certain syndrome events that are rare, but have to be handled. As you scale up the system, as you have basically a larger number of logical qubits, and you're going to implementation of algorithms that needs very deep circuits, these rare events become, they're happening all the time. So you need a heterogeneous approach for decoding of different, pre-decoder, like more standard decoding and more fancy hardware for rare events. And that means that the entire architecture should account for that. It's just a different workflow for when you scale the system to really, let's say, tens of thousands of logical qubits or bigger systems. And those are definitely not they are beyond GPU and most likely FPGAs.
Maybe I can translate Masood's comment a little bit. So as I was saying, that you have this classical hardware that is running these decoding algorithms. And so there is a lot of variability in how quickly the decoder spits an answer. Okay, so imagine it's like, okay, there was an error on a few qubits, very simple thing. You send it to the decoder quickly solves the problem, tells you how to fix it. But now imagine there were errors on many, many qubits. It could take a very long time for the decoder to actually find the solution. And until then, your qubits are waiting there. Of course, you're doing other things with them to keep them alive, but then you have to wait till this decoder is done and then apply corrections. So one of the ideas people have had is that, how about I build a pre-decoder which catches all the easy things, is very fast in the connection to your QPU. So for all the easy errors that happened, I quickly solve it, apply a correction. And then when the pre-decoder gets an error, which is like, oh, this is it's going to take a while to solve this problem, it sends it to a much more heavy hardware, specialized hardware, where it does all the decoding and then sends it back. So basically, you classify your error events as easy to solve, hard to solve. The easy to solve run on some lightweight hardware, and the hard to solve run on more heavyweight classical hardware. Perfect. So maybe I'll make a clarifying comment to help. So as we agree, right, that the tight integration of classical resources is absolutely essential here. The point is that pretty much I consider this part of QEC research, like QEC hardware design architecture research. And in fact, like pretty much every QPU vendor is going to do this. Like it's not something that we are cooking up. This is how the community thinks about it, because let's say I allocate a bunch of FPGAs to do decoding. Most of the time, most of them are not running, because most of the time you don't get that many errors. So what you really want to do is, from the hardware design part, from the system architecture point of view as well, you want to just allocate a couple of them as these pre-decoders that are always fixing your small problems and only kick in the higher ones when the
But I mean, to that point about the easy hard
Yes.
decoding part. So, just a simple question: the designation of easy hard
Yes.
is also going to take some time, and does that
So in this case, I'm using a very simple definition in the sense that we have a pretty good sense of what are easy syndromes versus hard syndromes, which is like kind of the error length, the chain length of the errors, which is how many errors, roughly speaking, happened. And of course, you could, take this to the next level, being like, can we really classify all errors and anticipate how much time it would take to solve the problem? And as we know, generally in computer science, these kind of problems are like, to know how much time it takes to solve the problem is as hard as solving the problem.
Right, yeah,
So I
right.
understand
That's
your
what I was going for.
exactly.
Yeah.
But in this case, we have a pretty good sense of how these classifiers work. They're a bit more classical problems actually. The what the decoder is working on. So we have good classifiers for these things, and we can allocate lightweight hardware and heavyweight hardware.
Okay. So I
But
have one. Oh, sorry. Go ahead, Masood.
Yeah, I just want to mention that was a great question. There is, in fact, you have to, categorize it into three level of hardness of easy, intermediate, and really hard. Generally, this can be mapped to solving NP hard problems in worst case scenario. And there's just like you could say, polar distribution of errors in a sense that a lot of them are very easy, but the median kind of syndrome events could be intermediate hard, and which you need, let's say, GPUs, but then you might need to invoke like even probabilistic computing and even ASIC solution for certain really hard instances of syndrome events. So I'm saying that it's a three-tier hierarchy, I would say, when you scale up the system.
I had one other. I'm sorry.
No, it's okay. You were the next speaker, and so.
Actually, I have a lot. I have a lot left. So this is a really interesting conversation. Just kind of shifting, just a little bit on topic. The one thing that I'm also thinking about when we're talking about the latencies and the integration based on latency, right? I mean, I've seen some numbers, and the idea of like how much compute would be available in late. But what I'm trying to understand is, I'm not to be like so tactical, but what I'm really curious, can we get some sort of idea of what sort of latency would be actually involved for a particular error correction at so many logical qubits, whatnot, the hardware required, but the distance required? I mean, literally, based on that time, I would be very curious, because both the size of the compute and the distance is making me wonder, first of all, what does that actually look like? And then if it's close, but a whole lot of compute, and the compute all has to be close, are we now looking at like crazy stuff of like quantum computer with the HPC around it, in disk or even three-dimensional? I mean, we're starting to stack up data centers, so I'm just like, what? Sorry, I'm rambling a little bit, but I'm really just kind of curious if we've got any projections in that.
I think there is this paper from NERSC people where they estimate, like, let's say if you have 100 logical qubits, the syndrome throughput is something like, depending on how what kind of decoder you're using, it's like 1 to 50 petaflop per second, I think. I want to say.
That seems like a large number, maybe, but.
So I think it's 1 to 50 petaflop per second. But this, yeah, I should double check, but I'm pretty sure it's in that range. So I can pull up the NERSC paper, and this is also on a surface code. So this is not on the more complicated error correction codes. And so but
a minute. Sorry. Okay, so
Yeah, I'm Paul at Alice and Bob, and I know we have these numbers internally to Alice and Bob. I don't know if I'm allowed to say them, but I imagine other vendors have these numbers in house too. So maybe we can compile them for the openQSE working group.
Can you just share whether like the order of magnitude that he's
Well,
mentioning
like
is that
Laura was asking, I think that answer depends on how many logical qubits your system has.
Sure.
Right,
Size of the patch or whatever.
Yeah. So it's not that high when you're talking about the first scientifically relevant 200 or so logical qubits. It's not that scary, at least for our system.
But it's because yours is noise biased and it's primarily bit flip errors. let's
Yeah.
say, and yeah.
Exactly. But you have to. But I'm just saying, like, your number depends on, for all the systems, it will depend on how many logical qubits you're talking about. But like I said, I don't know if I'm allowed to talk about it.
Okay, so we are about half an hour over time, and so I think this is a great discussion. Maybe we take the action to maybe dedicate one of the meetings to continuing this. I know we also have another action to create some definitions. Is that all right with everybody? But again, this is a community discussion thing, so if you want to keep going, raise a hand, and we can do that. I'm more than open
Can I
to.
make one point and I promise I will shut up? I'm sorry. I promise. Yeah, I know I'm the next speaker. So the one thing is the reason that I think that this is important, and again, kind of going back to, I mean, in my mind, again, thinking about facilities, right? We're not, the first system coming in might be, quote, lightweight, but it takes years and years to build centers and facilities for infrastructure, right? And so I'm always thinking, trying to think a decade ahead, if I can, and in terms of design, and then, to think about what's needed. So the kind of idea about, yes, we're going to get to scientifically relevant quantum computing in the mid 30s. How many logical qubits is that? I mean, that's why that paper is really good, that blueprint. But then what is the HPC or the classical compute needed? What is can we get an idea of the latencies? Any sort of, even if it's postulates, but we need to get, enough of an approximation that we can, as the facilities. I mean, I know that this is happening like in QBI and some other things, but that's also, some of that information is also not coming to people who are actively working on facility design. And I can think of, a regional one that's actually dealing with that issue right now, right? And so you kind of need that information. So this is kind of something that we, it would be really interesting to have these discussions.
Great. Okay. All right. Thank you. So with that, how about we move on? I have a proposal. So we have 3 things that we need to get done. Laura has a talk.
So, I mean, mine is kind of based on what I'm thinking about. It
Okay.
was just a conversation. So I can also shrink that or put it later.
Sure.
Why don't we go to the next one? Because I've been talking a lot.
So the next one is a we've allocated 30 minutes to have a conversation about how it is that we can overlap with the other work streams. And then the last 30 minutes is for us to compile a readout to the rest of the community. And so how about this as a proposal? What if we could you condense yours to about 15 minutes or less? Okay, and then we'll move on for 15 minutes and start the conversation about the overlap with the other work streams.